All right, so 8.3, testing a claim about the mean. So what's nice with 8.3 and 8.4 is the method used for these things is identical to the one from 8.2. All we have is we have a different critical value. So in this case, we're going to be using t-scores if sigma is not known and z-scores if sigma is known. So depending if it's one-tailed, two-tailed, so left-tailed, right-tailed. So if it's a two-tail, so if the claim is about equality, then this is going to be 0. So if sigma is known, or sigma, I should say, if sigma is not known, which happens more often than not, then these values are going to be your t alpha over 2, and this is going to be negative t alpha over 2. So you're going to be t-scores, you're going to use the t-table. If it's one-tailed, you're going to use t alpha. So say if it was let's say if it was like a left tail right here. So this is going to be a negative t alpha. Now remember that your table only gives you positive t-scores, so what you're going to do is you're going to take that value and just change the sign. So this would be t alpha, because remember the sum of the area in the tails has to be equal to alpha. Since there's only one tail, it's going to be equal to t alpha, but over here is negative because this is centered around 0. Now your critical value for your sample, so your test statistic, if sigma is not known, is going to be a t-score, so it's going to be equal to x bar minus mu all over sigma divided by the square root of n. So I'm sorry, not sigma, but s over the square root of n. So just be careful here with parentheses. So x bar minus mu all over s all over the square root of n. Now this is sigma not known. If sigma is known, then these would be back to z-scores like they were with proportion, and your z-score would be calculated using this formula over sigma divided by the square root of n. So t, just the only difference between t and z is this is the standard deviation of the sample as opposed to the standard deviation of the population. Now, more often than not, we don't know the standard deviation of the population, because if we're testing the mean, the standard deviation is found by finding the mean first, if you guys remember calculating that. So this is only when we arbitrarily set a standard deviation to a known number, like IQ, the standard deviation is 15, it'll always be 15. So in that case, we know the standard deviation, but not all cases we do. All right, so what I'm going to do is I'm going to go through some example problems, and we're going to show you that this is calculated the exact same way that you do proportion, except you use this equation in t-scores as opposed to the other ones. So earthquake groups. So I'm going to do number 16. So in data sets of earthquakes in Appendix B, they gave you the summary of statistics, like they had 600 earthquakes. The mean of that sample was 5.82 kilometers deep. The standard deviation was 4.93 kilometers in depth. And this is usually 0.01 significance level to test the claim that, that these earthquakes are from a population with a mean equal to 5. So we want to see if it's equal to 5. Now what we can see is that the mean is 5.82, and the standard deviation is equal to this. So, we can tell that this is already above, what the claim is. But is it far enough above? And, is it statistically equal, or is it, significantly high? Now that answer actually comes to do with how far this 5.82 is above this with respect to how many standard deviations. So since the standard deviation is relatively high, I think we're going to be good, but we'll know in a second. So let's set it up. So so this is number 16. So number 1, what we have to do is we have to talk about the claim. Well, the claim says that the claim is about the mean. So instead of having p here, you're going to have mu here instead. And they said the mu is equal to 5. I know it's 5.00. I guess we could just do 5.00 kilometers. Then we have to do what's the opposite of that. Well, the opposite means you're either equal or you're not equal. So the mean is not equal to 5.00 kilometers. So now we go to number 3 and figure out what the null hypothesis is and what the alternative hypothesis is. Now remember, these colons just mean that the null is whatever. So This is going to be the one with the equality. So the one with the equality is the top one. So this is equal to 5.00. And the one without the equality is going to be the alternative. So this is 5.00. So you can see that the claim actually is the null in this case because the claim is about equality. Number 4, we have to talk about alpha. Well, alpha is equal to 0.01. And I need to kind of know if I'm going to use T alpha or T alpha over 2 or negative T alpha. So where that comes from has to do with the tail. So if you look at the alternative hypothesis, I know that not equals means that you're either too far above or too far below. So I can see that this is a two-tailed situation because of the not equals part. So the tail comes from the alternative. So I'm going to draw down here number 6 again. I know I'm doing a little ahead, but I like it this way. So number 6, when I look at a T distribution, which looks a heck of a lot like a Z distribution, because they're calculated almost identically using S as opposed to sigma, this is going to be equal to 0. Now, since we're two-tailed, the sum of these tails is going to be equal to that 0.01. So, each one of these is 0.005, and this area is also 0.005. So what I need to find is these critical values that live in these particular spots right here. Find those critical values. So what I'm going to do is I'm going to go to the T tables, and we'll be able to find those things. So let's go ahead and find those right now. So the T table is in Appendix A. So if you're looking in your book, it's going to be page 686. So here's our T table. So what? I have a handout for that. We'll use the handout as opposed to the book. So it's also right in the sheet that I gave you for your exam. So our T distribution is this one right here. So it looks like this. So remember, read it correctly. Like it tells you what it is. So what I'm looking at is the area in a single tail. So the area in a tail happens to be the 0.005. And also to figure the rest out, I need to know what the degree of freedom is. So what this says, I think we had 600 earthquakes. So the degree of freedom would be, it's at 600 earthquakes. So the degree of freedom would actually be 599. Now your table doesn't give you that, so what I'm going to do is I'm going to take the closest number to this. So I'm going to actually use the 500 as opposed to the 1,000. So, yeah, unfortunately the table's not going to be nearly as accurate as technology, but we'll get there in a little bit. So I'm going to use that 500. So my T score is going to be 2.586. Now I got to use this and its negative because the 2.586 represents this number. So since it's two-tailed, I have to use the positive Z alpha over 2 and also the negative Z alpha over 2, so also negative 2.586. Now I know these tails and where they live, I need to find my test statistic. My test statistic still comes from my sample, so this is my sample value. And it's calculated because sigma is not known by a t-score, so t is going to be equal to x bar minus mu all over s divided by the square root of n. So x bar is they're testing to mean about x bar is the value that was given. So they said the claim was that, or the value that was given, x bar is 5.82, comes from the sample. So this number right here always comes from the sample, and this number right here always comes from the claim. Honestly, the numerators look very kind of similar to the proportion as well, like sample here, claim here. All divided by the standard deviation of the sample, which is going to be 4.93, divided by the square root of 600. So be careful here when you're popping these things in your calculator. Your parentheses are extremely important, so that has to be in parentheses and that has to be in parentheses. If you don't do it, it's going to be, you didn't see any of that. So let me re-say it again. So this is going to be the equation. So x bar minus mu s divided by the square root of n. This number here always comes from your sample, and this number here always comes from your claim. So then this is s, and this is the square root of n, which is 600. Don't forget to use parentheses here. It will not come up with the right answer if you do not. So what's kind of nice is you can just, you can plug in the thing exactly as it sits. I know I don't need the zeros there, but you can see it looks just like the equation that I had. Those parentheses hit enter. So my test statistic is 4.07. Ooh, that's pretty high. I was thinking that it was equal, but ooh, it's way out there. So this is 4.07. So when I look at this test statistic, I need to see where this thing lives on this chart here. So you can tell that 4.87 actually lives about right here, doesn't it? This is my t is equal to 4.07, which happens to live in the tail. So number 7, what we can say is we have to ask ourselves, do we reject the null? Remember the null's here. Or do we fail to reject the null? Well, it doesn't live in the null, so we have to reject it. So we're going to reject the null. We're going to reject the null. So number 8 comes down to, what we write. So if you want to go back to, refer back to 8.1, well, you might even have it memorized right now, but I'm just going to show you where this thing comes from. But remember that the way they give the answer is dependent on these questions right here. So it says the claim does not include inequalities. The top 2, the claim does include equality. So we're in the bottom. The claim includes equality. And we rejected H naught, so we're actually in the 3rd column here. So there is sufficient evidence to warrant rejection of the claim. Evidence to warrant rejection. Yep, warrant rejection of the claim. So again, what that means is we're rejecting null. So go over here, we're rejecting the null. That's not true. Remember, the null was the claim, right? And this was the alternative. So if we're rejecting the null, we're rejecting the claim. So the claim is wrong is kind of the idea. So there's enough evidence to reject the claim. All right. There's 2 different ways to do this. What I just did is I did what's called the p-value method. So you can kind of see it all. So I did what's called the p-value method. I'm sorry, the critical value method. If you want to do the p-value method, what you're going to do is you're going to look at, instead of looking at the critical values, what you're going to do is you're going to look at the areas. So I can actually find the area of this thing. So I can find a t-score that's at least closest to that. So if I want to find 4.07, what you're going to do is you're going to go to a t-table, and you're going to look for 4.07 somewhere in here. I don't actually see it. Maybe this might have to be done by, yep. Oh, here we go. What number is going to give us closest to it? So this makes sense. It doesn't give me an area. Yeah, I'm not going to be able to do it this way. I'll show you how to do it with technology then. So with z-tables, you can actually map back pretty quickly. So basically, we're asking about the area right here. What's the area equal to? Notice if the area is less than this, then it lives in the tail. If the area is greater than this, then it doesn't live in the tail. So one way you can use technology is you can go to statistics, you go over to tests. You can actually do a z-test if you want to do the previous section, and you can do a t-test if you want to do this section. And honestly, they're set up very different, very, very similarly. So when you look at this, you want data or stats? Well, sometimes they give you a list of data. If they give you a list of data, you can fill out L1. Remember, that's just stat, edit, go into L1, you can pop in the data here. But in this case, they gave us stats. So I can go over to stats, and I can pop in the numbers. This mu naught is actually talking about the claim, so the claim is 5. X bar was that 5.81, right? 5.82, 5.82. The standard deviation was 4.93. N is equal to 600. And we are a not equals claim, so it's right here. So we are a two-tailed claim. Now we can draw or calculate. I'm going to do both of them. So when I calculate this thing, what we get is we get that, see that t-score of 4.07? It's that same number that we got right here. So you can find that t-score that way. Now you get a p-value of this number right here. So this is equal to 0.1234, 524. Yeah, so that's how small that is. That's that number right here. That's that p-value. So that's that number right here. That's that p-value. So that p-value represents the area. And notice how, again, this area is less than this area, so that means you must have lived in the tail. So that's another way you can look at it. So I'd like the critical value method because I don't need to use technology. I can just use a table, and I can always look that up. Let's go to draw. It's kind of cool. So if I go to stats, I go to tests, t-test, and I go down the same numbers, I'm going to go to draw. It's going to actually show me that picture. It's kind of cool. So it's centered around 0. I wonder if it's going to fill in the tails too. It's been a little bit since I've done this. Let's see. There's your t-score, and it doesn't do a very great job of it. It's because they're pretty far. 1, 2, 2.5, you can see those tails right there. But so it gives you your p-value and it gives you your t-value. So that p-value is not very great when we know it's actually this number. So really the calculate version is a little better. Okay. I'll do one more of these and then move on to the next section. So let's do a less. Whatever. We'll do this one. I'll do number 24. Trying to find one where you have data values they have to plug in, and then I wanted it to be less, but this is the one I can see. So, okay, so 24 says heights of supermodels. So listed below are these supermodels, and it says you use a 0.01 significance level to test a claim that supermodels have heights with a mean that is greater than the mean height of 162 centimeters for women in the general population. So what they want to know is, are supermodels generally taller? Is kind of what they're asking. So given that there are only 16 heights represented, we can conclude that supermodels are taller. But given that there are only 16 heights represented, can we really conclude that supermodels are taller than typical women? And in this case, I would actually say well, it does. Yeah, it does actually. It meets the requirement because remember that heights have a normal distribution. So the population comes from a normal distribution. Therefore, we're good. We can actually use that bell-shaped curve. So what I'm going to do is I'm going to pop in those numbers. I'm going to find all of the statistics, and then we're going to do it that way. So what I mean by that is I'm going to go into stats. I'm going to go to edit, and I'm going to put all those numbers into L1. So 178 and 177. Picked one that had less numbers. My goodness. Okay. Now I know I did that fast. So I'm gonna kind of cook through it, make sure I got it right. 176, 180, 178, 180, 176, 180, 177, 178, 178, 175, 178, 175. 170. Okay, good. So I got it out. So what I was doing is I was just clicking through just to make sure that they were all good. And there they are. Okay, so now what I can do is I can go to stat. I can go to calculate in one variable stats. There are now one, so I'm going to go there. So now I can get the mean and the standard deviation of the sample. So the mean and the standard deviation. So I'm going to go ahead and write that on my paper, and then we can answer this. All right, so what I know for number 24 is that x bar is going to be equal to 177.25, and s is going to be equal to 1.844. I'm going to go 844. I don't want to round too much right now. You like to round at the end. But if I was going to give these as actual answers on a test, if I ask you what is the mean, you got to go one decimal past the given data. So this would be 3 centimeters, and this would be 1.8 centimeters. So that's actually the answers I'd give you. But we're going to use those in the equation because I don't want to round right now. So you round last, technically. Okay, so step one. What's the claim? Well, the claim is about the mean, and the mean being greater than that average height. So this is 162 centimeters. The opposite then, so the opposite of that would be mu is going to be less than or equal to 162 centimeters. So 3, that means h naught and h1. Well, h naught's the one that has the equality, so it's going to be this bottom one, less than or equal to 162. And then that means this is going to be mu is greater than 162. And I can tell that, remember, that's the alternative that tells us what kind of tail this is, so it's right-tailed. So that means I'm only going to use a T alpha. And since it's right-tailed, since it's over here, I'm going to use positive T alpha as opposed to negative T alpha, which would be on the left. So it's going to be a positive T alpha. So 4, I know that alpha is equal to 0.01. Number 5, we're going to do our test statistic. So our test statistic, so this is from our sample. Basically, this is our sample value. Our t-score is going to be equal to x bar minus mu all over s divided by the square root of n. So the x bar, which is up here, this 177.25, minus the claim, which is 162.0, all divided by s, which is 1.844, divided by the square root of, I think there's 16 levels here. 16, so all over 16. So again, don't forget parentheses. That's what I get for that. Holy smokes. Sorry, it's a 33.08. That's a t-score. Remember, t-score is still a representation of essentially how many standard deviations. And geez, man, those girls are tall. So, okay, whatever. So, okay, so that's so big. All right. I need to double check because it's just so large. It's kind of dumbfounding. So. So what I'm doing, I'm just going to double check in my calculator. So I went to stats, and I'm going over to tests. I go to t-test. What's nice is I already have those values in L1 because I've already calculated them, and I'm going to go down to this has to be greater than, so I'm going to go over here, and I'm going to go and calculate and see what happens here. Yep, that t-score is right, 33.08. P-value of a very, very small area. So, all right. So when I look at number 6, what I have is I have this bell-shaped curve, and I know that we have a one-tailed situation, so that means this area here is 0.01. So that critical value can be found as T alpha. And remember, T alpha is going to be found by using the t-table. I have a degree of freedom of 15 because n is equal to 16, and an alpha, a tail, which is equal to 0.01. So I'm going to go to 0.01 and track it down to 15, so it's going to give me 2.602. So 2.602. Now when I did that t-test, found that standard deviation, that t-value, I'm trying to draw it way over here because we got something that's 30, something that's 33. So it is really, really big. Like this number right here is going to be way over here. So I think I may have to do like a little break to say that there's a lot more. So this is 33.08. Remember, the null is still the area of equality, essentially, around that 0. So again, we are going to reject the null. I'm going to reject the null. Now, number 8, when we go back and look, number 8 says that we have to look at those 4 pieces again. So in this case, our claim does not include equality. Our claim is something that's not included in equality. So it does not include equality, so it's top or bottom. But I rejected the null, so there's sufficient evidence to support the claim. So sufficient evidence. Okay, so when we go back, let's just make sure that this makes sense. So what I did is, I know it lives in the tail, right? Since it lives in the tail is correct. It lives in the tail, and the null is incorrect, so it lives in the tail. Now if I go map back to where this came from, well, the tail actually came from the claim, so that means the claim is correct and the opposite is wrong. So that's why we are accepting the claim, because it lives in the claim. Because it lives in the tail, and the tail is the claim.